This paper is about supersolidity, which is a very intriguing phase of matter that shows at the same time frictionless flow and crystallization. And the main result of the paper is to show that what is called a spin-orbit coupled Bose-Einstein condensate. So Bose-Einstein condensate is subjected to a special type of light that introduces coupling between two different spin components, and the momentum of the atoms can become a supersolid. So the idea that spin-orbit coupled Bose-Einstein condensates could be supersolid is quite old, but there was also quite some debate on that, whether this was really a true supersolid or not. But the question was whether this crystallization was spontaneous or not, and whether this crystal that would form would have some dynamics on it, some excitations, would be flexible, or would be completely fixed by the light that induces the spin-orbit coupling.
In order to do this experiment, we have to start by making a very cold cloud of atoms. So we start with potassium atoms that are at room temperature, and they are very fast as a plane, and we have to slow them down, and we can use lasers for that. So we can use photons to remove energy from the atoms, and so we can slowly cool them down. And then eventually we will have a Bose-Einstein condensate. So when we have a Bose-Einstein condensate in our lab, we start to send two laser beams from two different directions. And we have two spin states in our system. Let's call them spin up and spin down. And now with these two laser beams, we can couple these two spin states to each other.
By coupling this in a mixture of two Bose-Einstein condensates, we've managed to create this spontaneous density modulation to make appear this stripe pattern in the Bose-Einstein condensate, which would be otherwise smooth and a bit boring. And this stripe pattern is kind of reminiscent of the structure of a solid, because it's some atoms are here, some atoms are here, some atoms are here, organized in a regular way, but that emerges spontaneously the way a crystal would.
A solid has excitations, basically vibrations of the crystal structure. The crystal structure is not really perfectly static, it's not like a crystal, but it can move, and it can change its spacing and so on. And then the question was, okay, if you have a supersolid, it should have all features of a solid. So it should also have these vibrations.
What we could see, so this supersolid, it's a cloud that has a density modulation. There are several ways of probing the supersolid. One could indirectly infer that there's this density modulation in the system, but we decided we really want to see the pictures of it. And what we could see is that the spacing of this density modulation was changing in time. So this is the most important dynamics that we have seen. We have seen other things, like that the total cloud size can change, and that we can have more or less fringes appearing in time.
This is much more than just seeing it. That is already a great success, because before it was not possible to see it directly. But also was really the key point was that we could probe the excitation. So demonstrating that this behaves really like a real crystal than vibrate. We managed to bring to the full analytical calculation, and this we are quite happy. So it's really show that for the moment this mixture model seems to explain really most of the physics, not just the formation of the crystal, but also the excitation. Without this model, we would have missed really the understanding of what was going on, and this is quite normally, it's very important for the understanding, but also simplify really the search of and the realization of the experiment.
And the conclusion is that spin-orbit coupled Bose-Einstein condensates are an excellent supersolid in this context. They are also very nice to understand conceptually. We think that we have, with this work, really brought some new platform for supersolidity in the field. We found a trick for seeing the crystal structure of this system for the first time, directly, and then we just take pictures and we see this crystal really moving around, breathing, basically. So really being dynamic. It's not something rigid, static, but something that is alive, let's say.